Hello, students! Today we are going to tackle a very important topic from your first unit, electric charges and fields, and that is Coulomb's law. Now, I know formulas can sometimes look a little scary, but I promise you, by the end of this session, this idea will be completely clear. You'll feel confident and ready for your exams. So, let's begin.
So, what's our plan for today? Simple. We'll start with a spark from a sweater, then use a really easy magnet analogy. After that, we'll look at the official rulebook for your exams, break down the formula, and I'll show you some common mistakes to avoid, the silent killers. And finally, we'll see how it all connects to the bigger picture. It's a very logical path.
Okay then, let's get started with our first section, a winter sweater spark. We're going to begin with a little mystery from our everyday lives.
I'm sure you've all felt this, right? In the dry winter months, you pull off a sweater and you hear that crackle crackle sound. Sometimes, if the room is dark, you can even see tiny little sparks. So, what exactly is happening there?
Well, that crackling sound is all because of something called static electricity. You see, tiny invisible electric charges build up on your clothes. And that sound, that's the sound of them jumping or discharging. And the force between these very same charges is exactly what Coulomb's law helps us understand. See? Physics is happening all around us.
Now, to really understand how these charges behave, let's use a very simple analogy, something I am sure all of you are already familiar with.
It's just like playing with magnets. You know what happens when you bring two north poles of a magnet close to each other? They push each other away, no? They repel. And if you bring a north and a south pole together, they just snap together. They attract. Well, electric charges work in the exact same way. Like charges, so a positive and a positive, or a negative and a negative, they will always push each other away. They repel. And unlike charges, so one positive and one negative, they will always pull towards each other. They attract. Simple as that. All right, so the basic idea is clear. Now, let's get to the official part. For your board exams, you must know the exact definition. This is what will get you full marks. So, let's open the rulebook.
Now, let's read this carefully. This is the definition straight from your textbook. The force between 2 point charges varied inversely as the square of the distance between the charges and was directly proportional to the product of the magnitude of the two charges and acted along the line joining the two charges. I know, it sounds very long and complicated. But don't worry, it's actually very simple once we break it down, which is what we'll do right now. And you know what? That entire long sentence can be summarized in this one simple formula. F equals K into Q1 times Q2 divided by R squared. Here, F is the force, Q1 and Q2 are our two charges, R is the distance between them, and K is just a number, a constant. This is Coulomb's law.
Okay, so let's put on our detective hats now and decode this formula. We'll do it step by step and you'll see just how easy it is.
It's very logical. Look at step 1, the top of the formula. It's Q1 multiplied by Q2. This just means if the charges get bigger, the force gets bigger. More charge, more force. Makes perfect sense, right? Now, step 2, the bottom part. This is the most important one. It's R squared. As the distance R increases, the force decreases. But it decreases by the square of the distance. That means if you double the distance, the force becomes 4 times weaker. It drops off very fast. And step 3, we just put these two ideas together with our constant K to get the full formula.
All right, theory is fine, but let's try a simple example to build some confidence. Imagine we have two positive charges. Each is plus 1 Coulomb, and they are placed exactly 1 meter apart in a vacuum. The question is, what is the force between them?
So let's just put the numbers in our formula. Q1 is plus 1 Coulomb. Q2 is also plus 1 Coulomb. The distance R is 1 meter. And the value of K in a vacuum is 9 into 10 to the power of 9. Now we just have to substitute all these values into our formula.
And when you do the calculation, what's the answer? A huge number. The force is 9 into 10 to the power 9 newtons. But wait, we are not done. This is very important. Both charges were positive, so they are like charges. So will the force be attraction or repulsion? Of course, it's repulsion. You must mention this in your exam answer.
Okay, now for a very special section that I prepared for you. I call these the exam silent killers. These are the small, silly mistakes that can cost you marks without you even realizing it. So listen very carefully. Okay, silent killer number 1 is forgetting the square on the R. So many students, in a hurry, just write R in the denominator instead of R squared. Don't make this mistake. Silent killer number 2, ignoring the direction.
Remember, force is a vector quantity. You cannot just write the number. You have to write whether it is attraction or repulsion. And number 3, applying the law incorrectly. Remember, this law works perfectly for point charges. Charges that are very, very small compared to the distance between them.
Fantastic. Now that you've really understood the law, let's take a step back and connect the dots. Let's see how this one idea fits into the larger world of physics. Does that 1 upon r squared part of the formula seem familiar? It should. It's just like Newton's law of gravitation, which is also an inverse square law. But there are big differences. Gravity is always attractive, whereas the electric force can be attractive or repulsive. And the other huge difference? The electric force is unbelievably, immensely stronger than gravity.
So why is this law so fundamental? Because if you understand this force, you have the key to unlock the next big concept in this chapter, which is the electric field. Think of it this way. Coulomb's law describes the force itself, and the electric field describes the area or the space of influence around a charge where this force can be felt.
Okay, let's do a quick summary of the most important takeaways. First, like charges repel, unlike charges attract. Second, the formula is F equals K Q1 Q2 upon R squared. Third, more charge means more force. Fourth, more distance means much less force. And fifth, electric force is a vector and it's way stronger than gravity. These are the absolute essentials you must remember.
And I'll leave you with one final thought to puzzle over. We just said that the electric force is so much stronger than gravity. Then why is it that when we look up at the planets, the stars, and entire galaxies, it is the weak force of gravity that is holding everything together? Why isn't the much stronger electric force doing that job? Think about that. It's a great question, and we'll explore it as we move forward. You all did a great job.